Greetings everyone! Today we are going to explore graphing ellipses at the origin. Now, there is another video for graphing ellipses translated and writing them, so make sure you're in the right spot. Let's get started. All right, let's talk about the parts of an ellipse. Importantly, we have the center point. Now, I don't have a consistent diameter length like a circle, and so we do have two lengths that are very important. The first length, the longest piece, is called the major axis. And then we also have the minor axis. Now in our class, we're going to stick to exactly horizontal and vertical values. It makes it a little bit easier, but of course these could be slanted lengths in the real world. Now inside the curve on the major axis, we're going to have dots. Individually, they're called a focus. Together or plural, they're called foci or foci. Depends on personal preference. Also, on the ends of our major axis, we have what's called vertices. Well, if I'm talking about the points on the ellipse on the major axis, I also have to talk about the points on the minor axis that are on the circle, and those are called the co-vertices. Notice how everything with the major axis sounds a little more important, if you will. Major axis, vertices, focus. Whereas the other direction, minor axis, co-vertices. We need all these values to help us, but we also need to work on memorizing which ones are which. All right, let's talk about the standard form of an ellipse. You are going to have this memorized, and you do have a spot for this in your notes. And so if you take a look at the numerators look just like the equation of a circle. It's still x minus h quantity squared. It's still plus sign. It's still y minus k quantity squared. That's the same as a circle. So use that to your advantage. It's like a circle squished. But here's the difference. This equation always needs to be equal to 1. Okay? Always. The second thing to note is that a squared, we have a denominator, is always the biggest value. A is always the biggest value. B squared is always the smaller value, the smaller denominator. Now let's talk about that A, B, and C value. A is the distance from the center to a vertex. I'll bring this up on another slide in a minute. B is the distance from the center to the covertex. So we have a spot in our notes. Let's fill this in. Let's talk about it. So A is the center to the vertex. We want to write that down. B is the center to the covertex. C, there's a spot to fill that in, is the center to the focus. So we're going to have 3 values, 2 of which we can count, or we can read, or we can interpret, depending on the information. You will always be missing one of the values. And so to calculate this, we have a special formula. So where it says formula for the foci, we want to fill this in. A squared minus B squared equals C squared. Doesn't that sound familiar? It's almost the same as Pythagorean theorem, right? But it's subtraction. Now I want to point out this relationship here because this is going to matter in future lessons. When the ellipse formula, it has a plus sign in the formula, and therefore to calculate, we use a subtraction sign. See how they're opposites? That matters, okay? We do have to work on memorizing. Consider possibly using note cards to start working on these things, but we definitely need to start working on memorizing these properties. Now, an ellipse can be horizontal or vertically orientated, and we have to know, how do you know which way? And we're going to stick to only those two options. Of course, there are more options in the real world, but let's just start with these two. Okay. Take a note. The numerators all look the same. All of this is the same, no matter what. Perfect. Easy to remember, right? Here's what's different. Your A value is the largest value. Whichever letter or variable it's under is your major axis. If A squared's under the X, then X is my major axis, meaning it's going to go horizontal. If A is under my Y, well, that's my y-axis, so it's going to be vertically. The bigger denominator determines the orientation. All right, so let's look at it vertically as well. You do have a spot. You could probably fill this in. We still have our center point. Our major axis runs vertically. Our minor axis runs horizontally. And of course, we have our foci, our vertices, and our covertices. If you need a moment, please pause this to jot these down. Let's talk about standard form there. It's going to look almost exactly the same as before. The one difference here is A squared is under the Y value because it's bigger and it's vertical. Therefore, the B squared is under the X value. Again, A is always center to vertex. B is always center to covertex. If you would like, this link can provide you with a great visual representation to compare circles to ellipses. What this link does is it allows you to sort of stretch. If I have a circle with a radius of 16, you'll notice we didn't talk about a focus in a circle because it is at the center. The moment I start creating a major and minor axis, look at that F1, F2. See how the wider the ellipse, the closer the focus is to the center. The skinnier the ellipse, the closer the focus gets to the vertex. And so it's just a neat interactive to kind of show that relationship. So consider bookmarking it and using it. All right, let's jump into our examples and our notes. Remember that today in this video, we are always at the origin, okay? Now take note, the formula for an ellipse is always equal to 1. If it is not equal to 1, you need to do something about it. And we are going to divide every piece by 25. You will always divide every piece by the number that is after the equal sign. What that's going to do is create these perfect denominators. Oops, 25 divided by 25 is 1. Let me fix that. Oh my goodness. Y squared will keep the 25. There we go. And we are equal to our 1 value. So you need to possibly rewrite the equation first. Now, in our class, I'm going to make sure that you get nice clean integers when you do that division. In the real world, of course, it would change things a lot. So let's talk about our major axis. Our major axis, our larger number is under the y. So we can say y-axis. Now I'm open if you want to say vertical or if you want to say oriented by the y-axis. Okay, that's up to you how you sort of describe that. Today and today only, our center is going to be at 0, 0, meaning it's a single x squared, y squared. Nothing's being added or subtracted. So I'm starting inside. Let's talk about the ABC because that is the new information we have to process. A comes from the larger denominator. This right here is a squared. Therefore, A is 5. B comes from the smaller denominator. B squared is 1. If I square root that, I get 1. C requires a little bit of work. You have probably some space to do that. We need to use our formula. A squared minus B squared equals C squared. A squared is 25. We're going to subtract B squared, which is 1. and that's going to be equal to c squared. So if I think about this, I'm going to have 24 equals c squared. I'm going to have to square root both sides to get my c value. Square root of 24 breaks down 4 and 6, so c is 2 square root of 6. If you need help reducing radicals, see another video, okay? So my c value is 2 square root of 6. All right, let's take these numbers and throw them on the graph. I need an ellipse. So A is the distance from the center to the vertex. I am orientated vertically. I'm under the y, so I need to go 5 from the center up and 5 from the center down. B value is center to covertex. I need to go 1 to the right and 1 to the left. That creates a very skinny ellipse. So try your best to draw those curves. All right, let's identify those points. My vertices exist. If I graphed it first, it kind of makes it easy. 0, 5 and 0, -5. Always write them as points. Your co-vertices are at 1, 0 and, -1, 0. Your foci, your c value is the distance from the center to the focus. We didn't graph that yet. Well, let's go back to that square root of 24. That's almost square root of 25, which means it's almost 5. That makes sense, right? I'm in this skinny ellipse, and my focus is just inside my ellipse, just inside on my major axis. That makes sense. It fits, right? If you miscalculate, it's not going to fit right. So let's write these as points. That means 0 left or right and 2 square root of 6 units up, 0, -2 square root of 6. We went up and we went down, and we have to account for both of those. All right, let's try one more at the origin, okay? First of all, I need to prepare my equation because it's not equal to 1, so we have work to do. We need to divide every piece by 72. I will always make sure they divide perfectly, so if they don't, something's up. Today, and today only in this video, we are at the origin, okay? We're not adding or subtracting anything. So 72 divided by 9, we're going to get a nice clean 8. 72 divided by 36 is 2. The larger value, the larger denominator is 8. It's under the x, so that means the x-axis is my major axis, which means we are orientated horizontally. Let's figure out our A, B, C. Our A value is from the larger denominator. This is A squared. Oh darn, I can't take the square root of 8 cleanly, right? I can't get A by itself easily, so I have to reduce square root of 8. We're going to get 2 square root of 2. Well, let's graph that before we worry about the other letters here. Square root of 8 is really close to square root of 9, right? And so we're just a little smaller than 3. So on the x-axis, or from the center, we're going to go a little less than 3 to the right and a little less than 3 to the left. And so if I write those as points for my vertices, that means I'm at 2 square root of 2, 0, and I'm at -2 square root of 2, 0. Right? We just don't have pretty vertices. Let's talk about our covertices, our b value. If this is b squared, oh, again, we can't take the square root of 2. We can't reduce the square root of 2, so we're going to leave it as the square root of 2, which is between the square root of 1 and the square root of 4, which means it's between 1 and 2. Oh my goodness. So between 1 and 2 would mean I'm about right here. This is a tiny ellipse. So if I write those as points, that means I'm at 0, square root of 2, and I'm at 0, -square root of 2, because I went up and I went down. All right, let's connect those dots. Try to draw the ellipse the best you can. Have those curves there. But now I need to do some work for my C value. Let's see how this works out with all these radicals. Our formula is a squared minus b squared equals c squared. Notice when I do that, you're literally just subtracting the denominators. That's it. So you wouldn't have to show work. You could just say, oh, 6 equals c squared. I need to simplify that. If I square root both sides, I get square root of 6. Can't reduce it, can't do anything else. Let's talk about how long about that is, right? Square root of 4 is close to it. It's a little bit bigger. So a little bit bigger than 2. If I go a little bit bigger than 2 on my major axis, look at where I'm at. That's perfect. I'm just inside the curve. That's where I need to be. So if I write that as a point, that means I went square root of 6 to the right, comma 0, and I want negative square root of 6 to the left, comma 0. Okay. Again, we're working with these radicals without a calculator because we don't want decimals. They're irrational. Also because we don't want to use our calculator, right? I will always give you numbers that you can sort of think through and know the about length. All right, so that is a longer lesson. Yes, conics have a lot of new information. They are going to take longer. Make sure to consider maybe rewatching without writing, right? That'll help you understand and take some time to really pay attention. As always, check out Google Classroom. Make sure that if you are looking for the additional ellipse video, right? If you're looking for translated, seek that out. Let me know if you have any questions. Seek out support in our resource center. And until next time, have a good one.